Example 8, the integral from 0 to 1, the natural log of x dx. The solution, we know that the function f of x equals the natural log of x has a vertical asymptote at 0, since the limit as x approaches 0 to the positive. The natural log of x equals negative infinity. Thus, the given integral is improper, and we have the integral from 0 to 1 times the natural log of x dx equals the limit as t approaches 0 to the power positive. The integral from t to 1, the natural log of x dx. Sidebar. Figure 11, the graph of y equals the natural log of x, and the area in positive x and negative y is the area equals 1. Back to the text. Now we integrate by parts with u equals the natural log of x, dv equals dx, du equals dx over x, and v equals x. The natural log from the integral from t to 1 of the natural log of x dx equals x the natural log of x on the interval from t to 1 minus the integral from t to 1 dx. To find the limit of the first term, we use L'Hopital's rule. The limit as t approaches 0 to the positive power of t, the natural log of t, equals the limit as t approaches 0 to the power positive of the natural log of t over 1 over t, equals the limit as t approaches 0 to the positive power of 1 over t over negative 1 over t squared equals the limit as t approaches 0 to the positive power of open negative t close equals 0. Therefore, the integral from 0 to 1, the natural log of x dx equals the limit as t approaches 0 positive of open negative t, the natural log of t minus 1 plus t close equals negative 0 minus 1 plus 0 equals negative 1. Figure 11 shows the geometric interpretation of this result. The area of the shaded region above y equals the natural log of x, and below is the x-axis is 1. And below the x-axis is 1. A comparison test for integrals. Sometimes it is possible to find the exact value of an improper integral, and yet it is important to know whether it is convergent or divergent. In such cases, the following theorem is useful. Although we stated for type 1 integrals, a similar theorem is true for type 2 integrals. See sidebar figure 12. There's a line for f and a line for g on the interval a to x on the x-axis. Back to the text. Comparison theorem. Suppose that f and g are continuous functions with f of x is greater than or equal to g of x, which is greater than or equal to 0 for x greater than or equal to a. Part A, if the integral from a to infinity of f of x dx is convergent, then the integral from a to infinity of g of x dx is convergent. Part B, if the integral from a to infinity of g of x dx is divergent, then the integral from a to infinity of f of x dx is divergent. We omit the proof of the comparison theorem, but figure 12 makes it seem plausible. If the area under the top curve y equals f of x is finite, then so is the area under the bottom curve y equals a g of x. And if the area under y equals g of x is infinite, then so is the area under y equals f of x. Open bracket. Note that the reserve is not necessarily true. If the integral from a to infinity of g of x dx is convergent, the integral from a to infinity of f of x dx may or may not be convergent. If the integral from a to infinity of f of x dx is divergent, the integral from a to infinity of g of x dx may or may not be divergent. Example 9, show that the integral from 0 to infinity of e to the power negative x squared dx is convergent. Sidebar figure 13. Here's graph y equals e to the power negative x squared and y equals e to the power negative x. Back to the text solution. We can't evaluate the integral directly because the antiderivative of e to the power negative x squared is not an elementary function. As explained in section 7.5, we write the integral from 0 to infinity of e to the power negative x squared dx equals the integral from 0 to 1 of e to the power negative x squared dx plus the integral from 1 to infinity of e to the power negative x squared dx. And observe that the first integral on the right hand side is just an ordinary definite integral. In the second integral, we use the fact that for x greater than or equal to 1, we have x squared is greater than or equal to x. So negative x squared is less than or equal to negative x. And therefore, e to the power negative x squared is less than or equal to e to the power negative x. See figure 13. The integral of e to the power negative x is easy to evaluate. The integral from 1 to infinity of e to the power negative x dx equals the limit as t approaches infinity of the integral from 1 to t of e to the power negative x dx equals the limit as t approaches infinity of open e to the power negative 1 minus e to the power negative t close equals e to the power negative 1. Therefore, taking f of x equals e to the power negative x and g of x equals e to the power negative x squared. In the comparison theorem, we see that the integral from 1 to infinity of e to the power negative x squared dx is convergent. it follows that the integral from 0 to infinity of e to the power negative x squared is convergent. In example 9, we showed that the integral from 0 to infinity of e to the power negative x squared dx is convergent without computing its value. In exercise 72, we indicate how to show that its value is approximately 0.8862. In probability theory, it is important to know the exact value of this improper integral. As we will see in section 8.5, using the methods of multivariable calculus, it can be shown that the exact value is square root of pi over 2. Table 1 illustrates the definition of an improper integral by showing how the computer-generated values of the integral from 0 to t of e to the power negative x squared dx approaches the square root of pi over 2 as t becomes large. In fact, these values converge quite quickly because e to the power negative x squared approaches 0 very rapidly as x approaches infinity. See table 1. There's two columns, one of t from 1 to 6, and the other column is the integral from 0 to t of e to the power negative x squared dx. Also see table 2, column t, and the column the integral from 1 to t of open bracket open 1 minus e to the power negative x close over x close bracket dx. And the t is 2, 5, 10, 100, 1,000, and 10,000. Back to the text. Example 10, the integral from 1 to infinity of 1 plus e to the power negative x over x dx is divergent by the comparison theorem because 1 plus e to the power negative x over x is greater than 1 over x, and the integral from 1 to infinity of open 1 over x close dx is divergent by example 1, open bracket, or by equation 2 with p equal to 1 close bracket. Table 2 illustrates the divergence of the integral in example 10. It appears that the values are not approaching any fixed number.